facendo si richiede
cosine of the first term 0 to x k of x prime dx prime cosine delta plus sine of the first term 0 to x k of x prime dx prime. Quantity and this delta, so I use this trigonometric sum. Okay, but now you can see something nice. What did we say about the wave function? It had to vanish at the origin. And let's look at these two functions. Which one vanishes at the origin? You have cosine of the interval from 0 to x when x is equal to 0 at the origin is cosine of 0, which is 1. On the other hand, when x is small, or x goes to 0, you get 0 for the integral and the sign vanishes. So this is the right term. So this wave function would be correct. This term would be absent. This is a term that you must make absent. Psi of x, without that term, would be a valid wave function. It is the wave function, therefore, the right wave function if we demand that cosine delta is equal to 0. So now we're imposing a very non-trivial condition. This wave over there, this contribution to the argument, to the angle here, this delta must be such that cosine delta is 0, in which case this term will disappear, and then we have the function psi of x, if this is true, is 1 over square root of k of x, that's the sine delta, which is another number, sine of 0 to x, k of x prime, dx prime. So we need cosine delta equal to 0. This argument gives you this wave function in a nice way here, which what it is. But we would have been able to find this even faster. If you just demand that psi at x equals 0 is 0, you must have this thing, the interval from 0 to a of this quantity minus pi over 4, that's the 0 cosine, and that's the condition we would find. The advantage of our rearrangement is that when that happens, the whole wave function looks like that, and that's kind of nice. That gives you a picture of the wave function, a fairly accurate picture of the wave function in this region. Not very near the turning point, but you got that. So what is this cosine delta going to 0? Well, then delta must be 2n plus 1 times pi over 2. So the places where the cosine is 0 is pi over 2, that's for n equals 0, 3 pi over 2, so for n equals 1, and it just goes the vertical axis on the unit circle. So this is where n equals 0, 1, 2, goes on and on. And this is a very wonderful condition. This says that the integral from 0 to a of k of x prime dx prime minus pi over 4. So actually, we have here the multiply by 2 and then you have pi over 2 and then 1 becomes n plus 3 quarters pi. It's Lorentz Sommerfeld quantization condition. Look, I box that equation because that really gives you the answer now. Why? Because you know that k is k of x is equal to h bar k square root of 2n e minus e of x. And if you know e, you know a. So you have now an integral. I'm taking example n equals 0. So you want the integral to be equal to 4 quarters pi. This is not changing the value of the energy of the computer. So this value of the energy, the integral of what I know, this is a known function, gives me this value. So this is a very practical way of finding the energy levels. It does give you the energy, the approximate energy levels, and it's remarkably accurate in many cases. It also has a little intuition. This is for n equals 0, would be like the ground state, n equals 1 first order excited states. And indeed, that makes sense because here this integral from 0 to a of k is the total phase of the wave function as we move from 0 to a. And that wave is a number of factor n times pi plus a little bit, so it has time for n zeros. The phase, as you move from 0 to a in the wave function, will have, the sine function will have n zeros. If the solution is satisfied, consistent with that solution. So that's it. We will continue next time, find the solution of WKB exactly. All right. We're going to complete our study of WKB today. There's a lot of important things we haven't said here, and in particular, we have not explained how it all works really in the sense of the connection formulas. That's the most non-trivial part of the WKB story, and in some ways it's some of the most interesting things that you have to learn from this. It's an opportunity to learn something about differential equation, Fourier transforms, and the limits of the quantities you can really compute. So we will begin our discussion with some reconsideration solutions. He lived in England for 19 years. He was the 7th Royal Astronomer. He was an astronomer from 1835 to 1881. He was located his work area in Greenwich. It's a little bit outside of London. And that's where astronomers were working hard to establish all the data associated with the prime meridian. France also tried to do that. The most important one, but at the end of the day, it all depended on which astronomers did the most work in measuring precise, accurate determination of times, motion of the moon, Jupiter satellites, all kinds of things that were pretty important at that time, especially also for manufacturing of good telescopes and good clocks. So Mr. Airy also worked in optics, and that's where he discovered these functions were studied, and they're very relevant to approximation. So let me remind you a bit of what homework and extend some of those ideas as well. So you consider a differential equation, the second psi, u squared equal u psi. I'm always surprised how a differential equation that looks so simple can be so intricate. But anyway, it is, and that's the Airy equation, and it shows up for this problem that you have, for example, an infinite flow and a potential that goes up like that. The bound states are controlled by solutions of this equation at the end of the day. This is after you clean up all the units and do all the work. But it shows in other places as well, and you probably found already that this psi function, psi of u, is given as a constant, that's an integral that came from Fourier transformations of e to the I k cubed over 3 e to the I k u. And so this is our integral, this is our solution of this equation, and the nice thing is that this integral tells you a lot about the function. It's a perfectly nice definition of the function. You may have noticed, and I think it was discussed to some degree in recitation as well, that the Fourier transform converts this equation into a first-order differential equation, because this becomes p squared times psi. Well, you know from showing the equations, this part of the differential equation comes from p squared. On the other hand, multiplication by x is the same as BDP in Fourier space. Therefore, you get a BDP of psi equal p squared psi equation, and that equation is a first-order differential equation. First-order differential equations have one solution. So you say, okay, I tried to do this by Fourier transform, and I'm getting just half of the solutions, and that's true. The reason is that the other solution of the differential equation doesn't quite have a Fourier transform, so it's a little more difficult to get at. But once you think of this integral, it is kind of useful to try to be a little more general and think of it in terms of the complex plane. The complex k plane. So here is the k plane. And this integral is over k from minus infinity to infinity. So this is the standard contour equation. We can call it the contour C1. When you're doing this integral, and you're doing this in the complex plane, you may want to consider that if you go off the real line, maybe things are even better. In particular, as you're integrating, u is a fixed number, it's a fixed coordinate. We usually think of u as real, but we could think of u as complex as well. And this integral has this factor, it's an oscillatory factor that becomes faster and faster oscillating with time. But the magnitude of the integrand is 1 at every place. It oscillates very fast, but the magnitude is 1. Not the best situation possible. You know, when you do that integral, you have the feeling that eventually you get 0 because it's oscillating so fast. But it would be nicer if you had a decay. So for that, consider that this function would be k if k is the imaginary part of k cubed is positive. K. Why? If the imaginary part of k cubed is positive, you have a k cubed would be I times a positive number. I times I is minus 1, so you get a suppression factor if the imaginary part of k cubed is positive. So if you're integrating over a region where the imaginary part of k cubed is positive, you will be in good shape. Now, if you think of k as the complex number e to the I theta k, k cubed would be this. And the imaginary part of k cubed is positive. K cubed is positive. Requires that this angle 3I theta k be between pi and 0. Why? Because if you have a complex number, any complex number, its imaginary part is positive if the argument of that angle goes between 0 and pi. if you get an imaginary pi positive for some angle theta k, if m of k cubed is positive for some theta k, it is also positive for theta k plus 2 pi over 3. Because if you add 2 pi over 3 to theta k, it changes by 2 pi, and therefore it's going to change. Sorry, I have an I too many here. The imaginary part of this requires the argument of this be between 0 and pi, or theta k between pi over 3 and 0. So actually here, I should draw 0 to pi over 3. This is at 60 degrees. And that's the region in K space where the integral is suppressed. Now we also said that this region is unchanged if you add 2 pi over 3. So if I add 2 pi over 3, that's precisely 1/3 of a turn. This is 30 degrees. It goes this area into this. And finally, if I add again 2 pi over 3, it goes into 30, 30, 30, and to this region. I guess this is a sign of nuclear material, hazardous materials. Or something like that. It's not hazardous or survive this lecture. So what's happening here actually is something quite interesting. For example, you're doing this integral here. If you started doing this integral, once you're far away, the integral over here is going to be nothing. Because you're very far away, and therefore you are in the region of absolute exponential suppression. We said this thing has a positive imaginary part, and therefore you have a suppression. It's k cubed. So it's becoming like e to the minus radius cubed. It's going to kill. So it's no problem to go up here when you get nothing. So what it means is that actually there's no similarities in the integral either. This integral that we've done here could have been done over this contour like that, and then you could have gone like that. You could do it mathematically. That's what I said. You could have gone like that. Or you could have gone here like this. Also, you're suppressed over here. And you're suppressed over here. And actually, when you come to the formation, you could have, instead of doing this integral, you could have come here and gone up like that. And done that. But also, you could get the same result. There's nothing. The integral is analytic here, so this, you can push it down and nothing goes wrong. Or you could have done even this integral, like that. Because the integral here is 0, and the integral here is 0, so you can like that. In fact, if you did this, if you put Mathematica would be trying to do this integral kind of does it, but complains a little. It's worried. It's not getting the answer right, because it's still the integral is still big. It's oscillating less than it's big. If you go here, I think Mathematica will convince. It will give you the same answer. So this is the power of complex analysis that allows you to do this integral in all kinds of ways. And there's something even more important about this that I will explain in the notes, but I can convey the idea here. When you prove that this is a solution, if you went to Fourier space, you had to do an integration by parts. And an integration by parts is always dangerous. And if you're trying to find a true solution of your problem, you have to make sure it works. P, the operator P, is supposed to be Hermitian. And here, what happens is that you turn this into dvp, and you have to fold back this factor. And here is where this discussion is very relevant. Because when you fold out this factor, you have to integrate. You can get contributions from the boundary, and you have to make sure those contributions are 0. Otherwise, you're not solving the differential equation, really. And the happy thing about these contours, and now that you understand this region, is that, yes, the boundary contributions are going to be 0 from the two sides because of the suppression factor. So this analysis actually turns it into a rigorous analysis, and the part that has to do with boundary conditions, the fact that the operations that you do are legal to try to solve the differential equation require, this is with details that I will not derive now, require precisely that e to the I k cubed over 3 e to the I ku vanish at the ends of the contour gamma that you're using to solve the problem. So if you're integrating from here to here, it should vanish at this end and at that end. Rigorously speaking, this thing only vanishes a little bit up. But this is what you really need for the equation to be a solution. So we have this integral, and with it's a contour gamma equal to C1, this contour over here, and the constant C equal to 1, psi that we have defined, psi of u, is in fact the area function of u. AI of u. I is not, I think I make tend to say I doesn't go like a subscript, it's to AI, like the first two letters of the name. So that's the function AI of u. And now you could ask, well, what is the other solution? Now, in fact, this diagram suggests to you that there's other solution because you can take other contours and make other solutions. In fact, yes, there are other ways. For example, if you did a contour, like this, yellow and yellow, this is not the same solution. It is a solution because of the general argument and because the endpoints are in these regions where things vanish at infinity. So the yellow thing is another solution of the differential equation. So the other area function is defined actually with this other contour. It's defined by taking the yellow contour like this. This is going to be called C2. The contour like that. It just comes parallel to this one and then goes down. And actually, in order to have a nicely defined function, one chooses for the function I of u the following: minus I times the integral over the contour C1 of the same integrand, so of it, always the same integrand, plus 2I times the integral over the contour C2 of the same thing. So the PI function is a little unusual in that it has kind of a little bit of the AI function because you also integrate over C1, but you integrate as well over C2. That guarantees that actually this second area function is similar to AI for negative u, and while AI goes to 0 for positive u, this one will diverge. There are expressions for these functions. I'll give you an integral. The two integrals that are famous are AI of u equals 1 over pi integral from 0 to infinity ek cosine k cube over 3 plus ku, and for pi 1 over pi, this is a little longer, integral from 0 to infinity as well, ek, and you have an exponential of minus k cube over 3 plus ku plus the sine of k cube over 3 plus ku, and that's it. It's kind of funny. One is the cosine, one is the sine, and it has these extra difference factors. So these are your two functions, and the relevance to our WKB problem is that they're necessary to connect the solutions, as we will see. But we need a little more about these functions. We need to know their asymptotic behaviors. Now, there are functions like the exponential function that has a Taylor series e to the z, 1 plus z squared over 2, and it's valid whatever this angles the argument of z is. That's always the same asymptotic expansion or the same Taylor series. For these functions, like the area function, for some arguments of u, there's one form to the asymptotic expansion, and for some other arguments, there's another form. That's sometimes called the Stokes phenomenon. And for example, the expansion for positive u is going to be a decaying exponential here, but for negative u, it will be oscillatory. So it's not like a simple function, like the exponential function has a nice simple expansion everywhere. It just varies. So one needs to calculate this asymptotic expansions, and I'll make a small comment about it, how to go about it. The nice thing about these formulas is that they allow you to understand things intuitively and derive things yourself. Here you see the two area functions, it makes sense. But another thing that's possible to do with this contour representation is to find the asymptotic expansions of these functions. They don't require major mathematical work. It's kind of nice. So let's think a little about one example. If you have the area function ai of u, that is of the form integral 1 over, well, it begins at ek over 2 pi, the integral over contour c1, make sure that the curve is C1.